Okay, so this is going to be an example of what the video should look like. And what I'm going to do this video is a short little presentation on basic circuits and how to figure out the different components of circuitry. All right, this is going to be the bare minimum. I'm not doing the whole unit. I'm not doing anything like that. I'm just showing you this is what I'm going to expect from you in your videos if you choose to do one. Okay, let's talk about basic circuits. When it comes to circuits, there are three different types. So we're going to start with the three types. First one's circuits. First one, and this is going to be the simplest one, this is going to be your series. Second one, it's going to be a tad bit more complex. That's your parallel. And number three, this is going to be your complex. Okay, before we talk about circuits, we have to talk about some of the terminology that's used. I'm going to expect you to provide the formulas, the explanations of the formulas, and to work out some of the problems. So when it comes to electric circuits, there's four things we got to know. All right. Number one is going to be Ohm's law. Ohm's law is resistance equals voltage over current. Now, these three terms we're going to be using over and over and over again. You're going to get very used to seeing them when we do the electric circuits, because that's the whole key to electric circuits. All right, now the three terms, let's go down through them. Resistance, okay, this is resistance to flow. Okay, now this is of the electrons as they move through the circuit. And by the time we get to that point, you will realize that yes, it's the electrons that actually move through the circuit, and that's it. Now, when we think about resistance, you need to think about it in terms of we're stopping the electrons from moving through. We're going to allow them to a point, but we're also going to, restrict that flow, hence resistance. So think about it as a rope going through your hands. If you apply a little bit of resistance, like your grip, what you're going to get is the rope going through fairly freely, okay? Won't hurt at all. Now, let's say that you're sliding down a rope and you're going fairly fast, or the rope is being pulled through your hands really fast, and you want to try to stop it. You have to really grip. That's more resistance. Now, if you do that, which I don't suggest you do, it's going to burn your hands really bad. So if you do that, that burn that you feel, that energy, that's the energy of the electrons, the rope, moving through your hands. The energy has to go somewhere. Resistors get warm. We'll talk about that more when we actually do this section in class. But resistance is basically just the resistance of the material to the flow of the electrons. Second variable that we talk about is the voltage. Okay, now this is voltage. And in class we'll learn that this is the potential difference. Now, potential difference, I'm going to show you how to talk about it in terms of potential energy. As the rope moves from here to here, it's changing position. Or if you want to go down with it, okay, so you go for potential energy and gravitational potential energy, it would go from here to here. It would lose energy as it goes down. As the electrons move through a circuit, they're going to lose energy. It's like rolling a marble down a hill. Think of electrons around. It was a marble. You let the marble go. As it goes down a ramp or it falls straight down, it loses energy. So the potential difference is the difference in potential energy between 2 points within a circuit. Last one is going to be current. Current. Now, we measure current in amps. That's what you're used to, is amps. Now, amps is just a flow of electrons. We're measuring the flow. How many electrons, how much charge, because every electron has a charge, how much charge is moving through a circuit at any one time. So this is going to be coulombs per second. Now that'll make more sense later on when we get to it, but I would expect you to explain that this is the charge of the electrons that are moving through the circuit in every second. It is a rate. Okay? Now, let's talk about series circuits. Those are the simplest ones. Okay? Now, when you have a series of circuits, think of it as a conveyor belt. It's a series of events. Things happen in line. So, if we have a series, draw one up here on the board for you. A series is going to be resistors in line within a circuit. Now when I draw a circuit, I'm going to start with this basic one here because it is the simplest circuit to draw. This is a series circuit. The electrons are going to go from one point and move all the way around. That's why I call it a conveyor belt. So that whatever happens here is also happening here. So we're going to get a chain reaction. You move here, then that forces this one to move, because you remember you got electrons filling up the whole thing. So as you go around, a series of events. Now these are the symbols for the resistors, and when you draw a circuit, you're always going to put what is the resistance of the resistance. So we're going to say that this one is 3 ohms, this one is 4 ohms. This is your switch, and this is your power source. So in my example, I'm going to have a 12 volt, let's call it a battery. It could be your house, it'd be 110 volts. And I've got 2 resistors. I have no idea what they are. One could be your cell phone, the other one could be, I don't know, a lamp in your house. Or, you know, if we're doing it in your car, this is the headlights, this is your radio. Yay. Doesn't really matter, because this is just a schematic drawing of what is occurring in this circuit, so we can share this knowledge with somebody else if they needed to work on it. Now, there's some things we don't know about this. First of all, we don't know what is the flow rate or the current within this circuit. So, in order to find the flow rate, the amperage of the circuit, we have to find what's called the resistance of the circuit, the equivalent resistance. So in a series, this is why they're really easy. You take all of your resistors and you add them up. So in this case, we're going to take first one we run into, 3 plus 4 equals 7. So the resistance total of this circuit is going to be 7 ohms. That's the symbol for ohms. Now that we have the resistance for the circuit, we acted like this is 1, and we have the voltage of the circuit, we're going to go back to Ohm's law. Resistance is equal to voltage over current. So we plug it in. What is the resistance of the circuit? The resistance of the circuit, we learned, is 7, equals, what is the voltage of the circuit? 12. And we don't know what the current is. That's what we're trying to find out, is what is the flow rate of these electrons through here. So 12 divided by 7, I'm not going to do the math there. Surely you know basic algebra. So 12 divided by 7, that's going to give you somewhere around 1.8. Let's call it 1.8. Sort of equals 1.8 amps. Now the key here is that when we find that is the current for the circuit, we're saying that that is the current going through every single part of that circuit. So every second there are 1.8 coulombs, because it's coulombs per second, 1.8 coulombs of electrons charge going through this chunk of wire, this chunk of wire, this chunk of wire, this resistor, that chunk of wire, so on, so on, so on, even through the switch. 1.8. You can't have a conveyor belt with 2 different speeds at 2 different points. If you put it on the conveyor belt here, it's going to travel at the exact same speed as something else here. Series circuits. Now, they are simple, but they have a downside. The downside is, if I were to break this resistor, okay, now the path is broken. The circuit is broken. It does not work. If you've ever seen the National Lampoon's Christmas Vacation, and they told Rusty, hey, we got to check every one of these bulbs. That's why, because the early Christmas bulbs were all lined in series, because it was simple to do. If you lost one Christmas bulb, you lost the whole string of them. So they started doing them in a different fashion, and that's parallel, and that's what we're going to talk about next. But this is series circuits in a nutshell. Okay, let's talk about parallel circuits. Parallel. Now, in a parallel, unlike a series, there's multiple paths. So, first thing I'm going to do is I'm going to draw some resistors here. And I know what my goal is. So I'm going to draw my circuit lines in now. Always got to have a power source. And you always have to have a switch. In this case, I'm going to stick with 12 volts. I'm going to say that this is a 2 ohm. This is a 3 ohm, and this is a 4 ohm resistors. Okay, now, the cool part about a parallel circuit is that notice we have multiple paths. The electrons can choose to go this way, they can choose to go this way, they can choose to go that way. They're all going to go through. It's just what path do they take. Electrons are all the same, so they don't really care. It's just whoever gets there first. Think about water pouring out onto a board that has 3 holes in it. Okay, you're going to drain the water off the board with 3 holes. We have the same thing, only this is a small hole, because notice it's 4 ohms. This is a medium hole, notice it's 3 ohms, and then this one has almost no resistance, so it is 2 ohms. Everybody good? I hope so. So, if I lose, and this is the beauty of a parallel, if I lose, say, the 3, I plug that hole. Water can still escape, electrons can still get around. So, that's how they wire Christmas lights now today. This is also how they wire your house. So if you blow a bulb in the kitchen, it doesn't shut down the stove. Everything in our homes is in parallel. Excuse me. Now, to figure out some things about this one, we need to know what is going on in this system. Okay, so we start here with the 12 volt. We know that, just like when we were doing the series, and we are going to be using Ohm's law. Again, resistance equals voltage over current. So, the difference here is that when you're doing the resistance, the equivalent resistance of a parallel circuit, you don't just add them together. You do add them, but you got to do something to them first. So the first thing you got to do is you got to get the inverse of all of them. So it's technically, or actually, 1 over 2 plus 1 over 3 plus 1 over 4. And then that answer is also inverted. So what we've got is 1 over 2, and the equivalent in decimal is going to be 0.5 plus 0.3 plus 0.25. We add all that up. So we got 0.8, 10, 5. So that would be 1.05. Everybody agree? I hope so. I usually did this pretty well. Now, then we have to say, what is the inverse of this? 1 over 1.05. Now, obviously, it's going to be less than 1 because you're dividing, but we're just going to call it 1 for this example. In your videos, I'm going to expect you to actually have the math. This is nothing more than showing you what these things look like. Okay, so we're going to guesstimate this to be at 1 divided by 1. Now, that is 1 ohm of resistance. That means that this circuit itself has 1 ohm of resistance, and that makes sense. We're not trying to shove all of the electrons through one resistor or this one. We're actually splitting the whole thing through 3 resistors. Now, when you do your math, you're going to find that if this is bigger than any of these, you did something wrong. Okay? Self-check is built into this math. So, we've got an equivalent resistance of 1 ohm for the circuit. We go back to Ohm's law. We say the resistance is 1. We know the voltage is 12. The current is I. So 12 divided by 1. This has 12 amps. So in other words, this has a lot of electrons going through it. Okay? And that makes sense. You're going to power your blow dryer. You're going to power your DVD player and your TV player. I mean your TV, whatever you're watching your Netflix on or your DVDs on. So that's what we've got going on here. Now, 12 amps. That means we have 12 amps going from here all the way through. Okay? But since we have different resistances, that means we don't have the same flow rate. Obviously, this thing that resists a lot is going to have a much lower rate of electrons going through than, say, this one. Now, what we do know is that in a parallel circuit, we have 12 volts here, 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 here. All the electrons are going to lose the same amount of potential energy going across. That's a rule in parallel circuits. But what they're not going to have is the same amperage. So if we make a cool little chart, and let's say we label this one A, this one B, and we label this one C. Now I always label in letters because that keeps me from getting confused with the numbers. If I say resistor number 1, resistor 2, resistor 3, okay, well 2 was a 3 and 4 was, no, letters. Okay, letters make your life easier. And we make a little chart here, I, R, V, and then we say A, B, C, because we got 3 resistors. Now we write down the things that we know. Okay, now this is working smart, not hard. What do I know about resistor? A, I know that it has 2 ohms of resistance. B has 3. C has 4. Now, because of that rule, the potential difference for every one of them is the exact same. That means it's 12, it's 12, it's 12. Now, using Ohm's law, again, okay, there it is right there. Okay, using that, resistance is equal to voltage divided by current. So that means it's basically voltage divided by resistance. Flip-flop those two. So 12 divided by 2 equals 6 amps. 12 divided by 3 gives you 4 amps. 12 divided by 4 is 3 amps. Now, if we do our math right, these should add up to 12. We're going to get little mathematical differences here. My mathematical difference is right there. That's my mathematical difference because I ballparked it. Again, when you guys are doing yours, I'm going to expect you to have the right answers and the right math and explain things like why I don't have the same thing going on here. All right, so that's parallel circuits. They're not hard, but they are more difficult than the series. Okay, let's talk about the last one, and that's going to be your complex circuits. Okay, now a complex circuit gets its name not because it's hard to do, it's because it combines a series with a parallel. So if we go with a very basic one, so I start here, and when I draw my circuits, I usually do something like this, if I have some idea what's going on. Volts there. Now I know I've got to have a complex, which means I have to have a combination of series and parallel. So I'm going to do this. I'm going to put one here. I'm going to put one here. I'm going to say that this is the 2 ohm, this is the 3 ohm, and this is the 4 ohm. Now, these are the exact same resistors that I used in the parallel example. The thing is, it's not the same configuration. And because parallel and series have different methods for figuring out the equivalent resistance of the circuit, those numbers that we figured out for the parallel won't work in this one. All right? So, first thing we have to do is we got to get the equivalent resistance. Now, in order to do that, target number 1 is get rid of this parallel nightmare right here. Remember, we want the resistance of the whole thing. And if we look at the path of electrons, it goes around like this, and then it gets to this ugly thing here, and then it goes back to nice simple thinking. So the first thing we're going to do is get rid of this parallel. So we're going to find the equivalent resistance of that chunk. So whatever it may be. So we got 3 here and we got 4 here. Now remember, we got to go 1 over 3 plus 1 over 4 equals something. 1 over, and I'm going to call it x, whatever. So 1 over 3 is 0.3. 1 over 4 is 0.25. Add those two together, you get 0.55. 1 divided by 0.55 is going to be 2. Let's just call it 2. 2 ohms. All right, now I realize that my math is not correct. Again, this is for example purposes, and we're in class, you'll figure that out also. All right, so we know that this is now equal to 2 ohms. Now, what I've done with this is I've now taken this and put it in series with this 2 ohm resistor. Now we can use the simple method, series. So I say 2 ohms here plus 2 ohms here equals 4 ohms. The resistance of this circuit is 4 ohms. Now I go back to Ohm's law. Resistance equals 4, just got it here, is equal to voltage over current. So 12 divided by 4, that means this has 3 amps. Okay, so now we've got the amperage for the circuit. Time to build a chart, because I'm going to ask you to tell me everything about everything on these. Okay, so if we look back at our other chart, I, R, V. No particular order. That's how they came to me in my head. So A, B, and C. Let's label them. A, B, C. So A, what do I know about it? I got 2 ohms. B, I got 3 ohms. C, I got 4 ohms. Okay? Now, I don't know what the voltage is across here because in voltages in series, they're going to be different. You got to split that potential difference. Think about a roller coaster. You go up the first hill, and then now you don't really know how much energy you have left, but you know it's going to be less, and then you got another hill, right? Okay, all I know is that this voltage has to add up with this voltage to the source voltage. And I don't know what that voltage is, but I do know what the current is. Because remember, it's a series, thinking of it this way, using that 2 ohms, it's a series. So whatever I got, 3 amps, I got 3 amps going through here, and I got 3 amps going through here, and 3 amps going through the switch and everything else. So I do know that the current in A is 3. Awesome. Now, if I've got a current of 3 and a resistance of 2, looking at Ohm's law, current, resistance, I know that the voltage is 6, because 3 times 2 equals 6. Okay? Now, up here, let's look at this parallel part. Now, I know that this thing, and this is the thing, we start out with the complex, you start out small, and you work to the big circuit.
Freshman advisors need to report to room 402 and not the patio commons for your meeting. Room 402 and not the patio commons.
I had no idea that that was going to happen. It's in my flow. I'm doing a good job. I'm keep going. So we've worked from the small to the big, and then we go back to the small. So we go through here again, and we say, okay, well, this thing right here is 2 ohms. That thing is 2 ohms. Now, if I was going to be doing this for real, for a grade, to show somebody else my work, I would be labeling this thing right here as, capital A circle, or, this would be little a, or something to that effect where I know that this thing, the small parallel, is A. So A has a resistance, A right here, has a resistance of 2 ohms. Now I know that A has a resistance of 2 ohms, so I say, all right, resistance is 2. I know that the current is 3 through this thing. So 3 times 2 equals, you got it, 6 volts. Now, that does not mean I got 6 volts everywhere, but it does mean that I got 6 volt drop from here to here. And just like in parallel, whatever the voltage is, remember the parallel thing? Okay, they all had the same volts, 12, 12, 12. So I know that this has 6 volts and this has 6 volts. Everybody in? So 6 divided by 2, 6 divided by 3, 6 divided by 3, because that's my voltage divided by resistance, is going to give me 2 amps. 6 divided by 4 is going to be 1.5. 1.5. We're good. I have every chunk of information for everything in this problem. Okay? This is what I'm going to expect you to do in this class. If you choose to go down this route and want to make a video proving that you know what's going on. For your conclusion, you have to remember to include all of these things in your videos. Number one, you got to have the terms. What are we going to be using? Okay? If you got resistance, you better explain to me what resistance is. If you're talking about the variables, we're using a formula. Tell me what the variables are. Tell me what they mean. The formulas themselves, the formulas probably have a name, some sort of another. Tell me what is the name of the formula. Okay? And if it's something simple like it's the distance formula, okay. If it's free fall equation, that's fine. Just tell me what it is and tell me how these variables fit into the formula. Next thing is going to be the work. You've got to show me your work. Just like I showed you the little charts and I showed my work over here in various stages. I would love for you to have a little bit more order, but have some sort of order. Okay? It doesn't have to be perfect, but it does need to have some order. And you have to have some type of real world application. Explain to me how this is used in the real world. I used, for example, the Christmas tree lights. Okay? I mentioned your house, how the difference between a series and a parallel works. Okay? So, if you have any questions, feel free to ask me. Obviously, this is the last time we're going to talk about this, but I wanted to let you know and let you see what it takes to make one of these. Now, I did this free off the top of my head. I pick something later in the year. That way I'm not giving away anything to you right now. As you can see, I dressed up for the occasion. Got my tattoo artist representing. Had another take. I may throw that in at the end, just so you know what I was really wearing before I did this. Probably not administrator, something like that. So that's where we're at. Best of luck to you, and hopefully you all ace the test and you don't need to do this. Later.